Welcome back. As we all know, it is Friday. We have a shorter session today, so we're just gonna jump straight into it. And I'm just gonna kick off the timer. We were working on a problem yesterday called number of students that can't eat. And I have no idea why this isn't working. But maybe that has to do with this second example here. It seems like the TLDR is we have a set of students who prefer either uh, a square sandwich, which is denoted by a 1, or a circular sandwich, which is denoted by the 0. Right? Then we have the sandwiches that we have. And we have to figure out how many students can't eat. If a student can't find his preference or their preference, they don't eat anything. So, what's the problem here? The way we wrote it is that we could just match the ones to ones and the zeros to zeros. So if we count the students who want square sandwiches and the students who want circular sandwiches, we have 2 and 2. If we count the number of circular sandwiches and the number of square sandwiches, we also have 2 and 2. If we do 2 minus 2 and 2 minus 2, and then add those together, we get 0. For some reason, when we do that here, we don't get 3, which means something's wrong with the way we understand the problem, but I'm not really certain what the reason is. This has a lot of dislikes, though. Actually, it doesn't. So we take the square students. The number of square students are going to be the students that have 1, right, for their preference. And that's going to be 4, right, because we have 4 ones. 1, 2, 3, 4. Now the number of students who prefer circular sandwiches are going to be 2, and we have that 2 here. So how many sandwiches do we actually have? We should have 3 square sandwiches, which we do, and we should have 3 circular ones, which we also do. So if we do the square students, right, minus the square sandwiches, we should get 2. We should get, we have 4 students minus 3 sandwiches, we should get 1, right? Now if we do 2 students, we have two circular students minus 3 sandwiches, right? We get 0, because all the circular students were able to eat. The number of students remaining that were unable to eat Oh, I think I see where the problem is. The question is not asking us to match it. It's asking how far do we get. I see. It's asking how far do we get until we have a blocking. So we have a blocking incident. For example, it's possible that many students won't be able to eat if we run out of students that should take away a circular sandwich off the top. For example, if we had 1 circular sandwich followed by 3 square sandwiches and our students were arranged and the students we had left were all square students, none of the students would be able to eat because we have no student which can take a top off of the stack, which I think means that the number of students left who haven't eaten, our answer here could be correct, but I think the cases change if we have circular students. If we have less circular students or less square students, right, then I think we just need to account for that blocking incident. So if we have less square students, if we have less square sandwiches, I'm pretty sure this is just a simulation problem now. Yeah. Because yeah, it is. So I think one of the issues we could try, let's try and see if we add the case to handle the blocking incident. Right? If we have less students, if we have less circular students, if we have less circular sandwiches than square sandwiches, it means we'll have a blocking incident. But the reason we won't be able to know how many students haven't eaten is because we actually have to run the simulation. So, yeah. At the end of the day, we're going to be returning student.length. We have two parallel arrays, right? If a student what I'm stuck on is just figuring out a way to know when we've crossed. Actually, we can make it simpler now that I'm thinking about it. So we need a function, some student can take top sandwich, and the way we'll just check that, we'll just return false, right, as the base case. As the case that when we know nothing, we don't get what we want, and then we're just going to iterate through all the students, right? For const num of students, right, if num equals sandwich, right, right? If a student matches the sandwich number, that means someone can take it, right? So we'll say while a student can take the top sandwich, right? Which we're going to pass in students and sandwiches sub 0. Right? Then we're going to keep doing the work, and the work is going to be if student sub 0 equals sandwiches sub 0, then we're going to say students dot shift and sandwiches dot shift. And then as soon as a student can't take the top sandwich, then we'll have to stop. if the student, right, equals the sandwich. Otherwise, right, what it should do is the sandwich to stay where it is, and the student, we should push, the student should go from the front of the queue to the end. So that works out. So we have destination city. You are given the array paths, where path sub I is equal to a tuple of city sub A and city sub B, means there exists a direct path going from city sub A to city B. Return the destination city, that is the city without any path outgoing to another city. So if we imagine this as a graph where path sub I is a vertice for each node, it's a vertice, we would have I vertices and we have path, we have I edges, basically. Actually, no, we don't know how many vertices we have. We just know how many edges we have. So we know we have an edge between city A and city B if it exists in path sub I. We need to return the destination city, that is the city without any path outgoing to another city. So pretty much we need to return the vertice without any with an out degree. Return the vertice with an out degree of 0. Return the vertice with the out degree of 0. Return the vertice with an out degree of 0. So we can do this in two passes. The first path, we could create a set of just all the vertices, and we can iterate through the paths again. And if there is an outgoing vertex, the remaining value in the set should be the destination city. So denoted with the out degree of 1, and with out degree of 0, we just have to make certain. So we have city sub A and city sub B, means there exists a direct path going from city A to city B. So if there to exist an outgoing edge, it means that it looks like we just have to take the union of the strings in city A or is maybe the disunion, the union of we need to find, there's an overlap between the strings in city A, the first tuple in city B. We want the string we want a string where there's no overlap. Because if there's no overlap, it means that we lack city A. So to do this, there's a couple of different ways to do this. But yeah, I think so we're just to like return vertice without degree 0. So we can get all the vertices by putting them all into a set, and then we can remove all the ones from the set. If it has an out degree, if it is city A. So we'll have a new set of strings, and actually we don't even have to iterate, we can just say new set we'll turn it we'll create a new set from a tuple of, actually we do need to iterate over them because we need all of them. There's so many ways to do this problem, which is pretty interesting. In fact, I think we could do what we just did, and then we could just return if set, right, does not have we loaded all of the city A's. We loaded all of the outgoing. If it has an outgoing vertice, it means that city A is the start of that vertice, right? And city B is the end of that vertice. To have no outgoing edges, it means that the node that is missing has no city A. So if the set does not have city B, I think we can return city B. This is not the one I was gonna do, but it looks like, I think this makes sense too. Yeah, there's like 100, like 1,000 ways to do this destination city one. Given a 2D grid size of m by n, given a 2D grid of size m by n and an integer k, you need to shift the grid k times. In one shift operation, element at grid sub I sub j moves to grid sub I sub j plus 1. Element at grid sub e. Grid sub I n minus So in the second bullet point, all the elements at the end of the columns move to where? Move to the front. The bottom right corner element moves to the top left corner. Bottom right corner moves to the top left corner. Grids of I, grids of J moves to one element to the right. Okay, I think I see what they're saying. Yeah, we move each element at grid sub I sub j moves one column over, right? We pretty much do all the cases of making sure that we slide each element to the right once. So grid sub I sub j plus 1, we move 1 to 2, right? Yeah, I think they just want us to write a function to move each element in the matrix to the right once. If it's going out of bounds, it should go to the next column, so on and so forth until the end, where if the bottom right element goes off out of the matrix, it should come back to the front. The way they're describing it doesn't make much sense, but I think the image examples make enough sense to write a function for this, but we only have 49 seconds left, so we'll just call it there.